told that you should never be the first speaker after lunch, especially on the last day of a conference or forum. But in any event, never follow an act with a bunch of cute kids. I don't know what I've done to offend Catherine, but I'm going to try to make it up. I'm going to be talking to you about something a little different, as will Randy, in that the experiences we've heard about so far have been of real hardware programs that actually successfully flew, and in the case of the shuttle, is still flying. And that's a very good experience base to talk about. I'm going to talk about the lessons learned in a program that is really very early in its maturation. We have completed on the Ares 1, our crew launch vehicle. We've gone through preliminary design review, PDR. One component, the J2X engine, has gone through CDR. So we're talking about relatively preliminary things. The Ares 5, in fact, is still in, I would characterize it as still being in phase A. So the lessons learned are a little bit different. However, I had the experience of working on the Saturn. I had the opportunity to work on the early days of the space shuttle. And so there are a lot of things that we learned then, and I would characterize this more as not the lessons learned, more the lessons that have been relearned. We've had, I hope everybody has had a good time and feels this has been beneficial. I think we've had a remarkable experience the last couple of days. If you heard nothing more than Tom Mosier's wonderful panel and Wayne Hale's panel this morning, heard the remarks of Tommy Holloway and others that are really revered icons of the human spaceflight program, I think you've already got your money's worth, and I hope that you will enjoy this as well. These are the topics that I'm going to try to cover, but that's kind of a partial list. I've got one slide for those, but there are various other things I'd like to discuss along the way that I just didn't list or have as a separate slide. And then at the end, assuming that we've got the time, there are three specific things, discussions that came up during the forum itself, kind of this versus that. And I'd like to have a chance to offer my personal perspectives on those. First, let's talk about the rebuilding the in-house capability. This was something that was very important to our previous administrator, Mike Griffin. He wanted us to rebuild that kind of capability. Now, I'll offer you a perspective from back in the 60s. The Von Braun team had come at the end of World War II to this country through Operation Paperclip, and they had been located in 1950 to Huntsville. They had hoped when they came to this country that they would get to work on a space program. Instead, they found we wanted to build a new generation of ballistic missiles. So that's what they did. But in 1958, January 31st, they successfully put the Explorer 1 into space, and that started our space program. They had moved to Huntsville in 1950 from Fort Bliss, Texas, where they had been working on the White Sands missile range. They came to Huntsville, and they converted Huntsville into Rocket City, USA. We had kind of a unique experience in that we had the people who had some 20 years of experience working together. They had been a team at Peenemünde on the Baltic coast at the German Rocket Development Center. They had developed, they had tested, they had manufactured the V-2 rockets that were used by the Germans during World War II. They pretty much had the world market on expertise in guided missile technology. They had that pretty well cornered. So we had the expertise of Von Braun. We had over 100 of his top assistants. If you looked at a Marshall Organization chart in the early 60s, it didn't look very different than a juxtaposed against a Peenemünde organization chart. You had pretty much the same people, same names doing the same job. So it was a remarkable opportunity for me as a very young man to join that team and have the opportunity to sit at the feet of those people. We didn't go to the contractors to look for expertise. The contractors came to Huntsville to find out how to build rockets, to find out how to build guidance systems, to find out how to build engines. We had that kind of expertise there. We could do everything for a launch vehicle at that time except launch it, and that's only because of the geographic position we were in. We didn't have a place to drop the stages. So we had a remarkable capability, and that's part of what we wanted to do, was rebuild that. Now, I don't want to, by suggesting that remarkable capability, not recognize the great capabilities that existed throughout the agency. This point's been made by others. I want to remake it. It is experts among the people and the teamwork between the people that makes systems fly. That's what makes systems work. We had a remarkable team of which I'm very proud in Huntsville. But at the same time, in NASA headquarters, we went through a series of extraordinary associate administrators. It was politically incorrect, but we call it the Office of Manned Space Flight. And we had a series of great administrators that made all the difference in the world. And we had people like George Miller, and then we had Dale Myers, and we had John Yardley, all of whom were giants. We had General Sam Phillips, who was an absolute legend, that was the Apollo program manager. At Johnson, again, you had the same kind of absolute giants. You had Bob Gilruth, and you had Chris Kraft, and you had Gene Kranz. You had Max Faget, who was literally a legend. And they, just as in Huntsville, they spun off a new range of experts. We spun off people like Jim Odom, who was not able to be here. He was here at the forum last year. He's one of the best engineers, one of the best managers, and above all that, one of the finest gentlemen that I ever knew. We had a lot like that. Bob Lindstrom, a lot of you would remember, George Hardy and others. That became real legends. Same thing was true at Johnson. And we had people like Tommy, who really, these were the people that made the space program happen. And they all worked together as a team. It wasn't one center versus another. All the centers had their jobs to do, and all tried to do it. So that's the point I want to make, is that we're trying to restore the capability. I'm speaking from the Huntsville standpoint, but all across the agency, we have lost some of those capabilities, the hands-on kind of capabilities that we used to have, and we need to rebuild all that, and that's part of what this program was all about. Another point I'd make from this chart is that we also need to learn how to build from one program onto another. It pictured up in the top left of the chart, you see a Saturn 1B. Now the Saturn 1B has a heritage. The Saturn 1B came from ballistic missiles that had been built for another purpose, and those ballistic missiles came from the technology and development program that was carried on during World War II. But we built something called a Redstone rocket that was 70 inches in diameter. It was what was the basis of the Jupiter C that launched the Explorer 1. We also had the 105-inch diameter Jupiter missile that was what was in Turkey at the time of the Cuban Missile Crisis. When we got ready we needed to build a stage very, very quickly. We took that 105-inch diameter tooling, and we built the center part of the Saturn 1 and 1B on that very tooling. We took the 70-inch tooling that built the Redstone, and we built 8 of those tanks. We clustered those 8 around the one. 4 of them plus the center core were LOX, and the other 4 were RP. We took advantage of what we had, and that was a very important lesson. People said you can't do that, but we did it. We had built a little Centaur stage that had less than 100,000 pounds of LOX hydrogen. It was the only cryogenic stage that ever been built. We built an S4 stage that had, the Centaur had about 50,000. We built one that had about 100,000 that we call the S4. Then we built an S4B stage that had 250,000. Then from that we built the S2 stage that had 1 million pounds of cryogenics. Today we build the tank, the external tank for the shuttle that has 1.6 million pounds. Each one of those built on the other. We didn't throw it away. We took that technology and we expanded on it, and we learned to improve on it. Several people have already mentioned through the course of the discussion the fact that the external tank, we had to take lots of weight out of that tank. in order to be, when we went to the 51.6 degree inclined orbit to have an international station that the Soviet Union could reach, or the Russians could reach, then we had to get more performance out of the shuttle. The best way to do that was to take weight out, because the external tank goes to orbit, or to the edge of the orbit, at a fractional orbit. So the best way to do that was to go to a lightweight material, but take that design and improve it. Louis Peach, in the early 90s, ran the advanced studies program within NASA headquarters, and he invited me to join him to work advanced transportation. And we invested money in a material called aluminum lithium. At that time, nobody had ever used aluminum lithium in space. It was very, very difficult to manufacture with it, because it was not easy to weld. It's hard to find anything to weld it with. We also invested money in developing a new technique called friction stir welding. That friction stir welding was used for the longitudinal joints to this day in the external tank. And it essentially brings the pieces together, and it essentially, by friction, plasticizes materials, and they flow together, and you have almost the same strength in your weld as you do in the base material itself. That was remarkable. When we got ready to design the upper stage for the Ares, we took that same material, that same technology, but now we developed a new type of weld machine that was basically had a self-backing, so that you didn't have to work from both sides of it. The machine itself could do that because of this self-reacting property of the new weld, and it was much less labor intensity. Each one of those things built on the other. We learned during the Saturn V program that you could have the same engine do more than one job. We had one J2 engine on top of the S4B stage that powered the S4B stage, which was the second stage of Saturn 1B, but then we used that same stage as the upper stage for the Saturn V. We took the same engine and we had 5 of those on the S2 stage. So we used that same engine for 2 different rockets in different stages. That same stage, it was the second stage of Saturn 1B, became the third stage, or Earth departure stage really is today's terminology, for the Saturn V. We built one thing on the other and took advantage. That is a very, very important lesson that we learned from the past, and it's not a new lesson in Ares 1 and Ares 5, but it is a reapplication of an old lesson. So I think that's a very important point to us. Next thing I'd like to cover is the subject of requirements. I think everybody here has at some point mentioned the importance of getting requirements. And ideally, what you want to do is get firm requirements just as early as it is possible to do it in a program. And the reason you want to do that is requirements don't cost much to start with. But the later you get in a program, then it becomes a change request. And the further you get in the design, the bigger the impact and the greater the cost. Now, very few programs ever have the luxury of laying out that ideal schedule and that ideal funding and that ideal set of beginning requirements and go from start to finish. If we could do that, then it would cost us a great deal less to do what we do in space. But because of the fact we don't have that ideal situation, the funding that we had to do the Constellation program was absolutely loaded wrong. We didn't have nearly enough funds early. Our funding, our available funds, came later. And that's not the right way to do it. You go very far off optimum when you do that. And then when your funding stream changes from year to year, then that adds even more to the cost. So nailing down your funding and nailing down your requirements early is very important. Now, there are some requirements you have to anticipate because they will emerge as you get into it. You will have requirements that will develop during the course of the program through nobody's fault, things you simply couldn't have known about. But your basic fundamental requirements, you want to get those down on paper just as quick as you can and then rigorously manage them and not allow requirements to change unless they have to be changed to carry out the mission. It says, as was said yesterday several times, that better is the enemy of good. And you don't want requirements to make the system better if it's already good enough. You want to fix your requirements fix them early, stay with them, change requirements only when it's necessary in order to make the system work. And there are examples of that. I won't take the time, but I could cite several where we've had to make some changes in the ARES program because of things we could not have anticipated at the start. Now let's talk a little bit about integration. A lot of people mistakenly think that if you have a box of parts, then you have basically a vehicle. There's a lot of difference in having a rocket engine or a couple of rocket engines, solids, liquids, whatever, having a few tanks, somebody's got an avionics system. Putting all those things together is tough, very, very hard. But you can make that job a lot easier if you plan for it from the start. So for example, in the ARES 1, we're building both physical and analytical models of the vehicles so that we have a good idea of fit and function before we try to stack those things together. In the past, even with the best of tools available at the time, people took parts that looked like they should fit together and they found that they did not fit quite the way they were intended to, and then real-time fixes had to be done. Well, we built actual physical models of things, a mock-up, for example, of the entire thrust structure, the interstage, those kinds of things. We put people inside to see if there's enough physical room to move around, to make repairs, that kind of thing. We do that analytically. We make sure all the bolt holes line up, all the clearances are what they ought to be. That will make the integration job easier. But if you don't plan for that at the time, if you just build the parts and then say, well, we will put those together and we'll make them work, you learn that that is in the long run going to be a much longer, drawn-out process. And once again, it comes back to money. It's going to cost, when it takes longer, it's going to cost you more. We did that. We learned a lot with ARES 1. Some people question, well, it was our ARES 1X. Some people question, was ARES 1X something we really needed to do? Was it just a stunt? We learned an enormous amount in putting that vehicle together. We had to mate the simulated upper stage to the first stage. We had to find avionics that would work, that would control the flight. This all had to interact with the ground processing systems, the way the things were mounted. All of those things had to fit together, and all more important than that, they all had to work together. And we learned things about the processing plans for the ARES 1X that were surprises to us. These things are going to happen. So vehicle integration is something that needs to be taken into account really right from the start. Now this is kind of a follow-on to the first chart, and that is one of the things that was the administrator's intention was that we get a lot of hands-on experience, not just paper experience. Now at the time I went to work for Marshall, the quality of the young engineers and professionals that we were hiring was not nearly as good as it is today. I'll be the first to admit that. The kids that are coming out of school today have better analytical processes, they have better tools, they understand a lot of things that we didn't understand, that we had to learn. Because, in fact, there was, at the time I started with Marshall Center, there was no such thing as an aerospace engineering department. There was aeronautical engineering, there was mechanical engineering, there wasn't aerospace engineering. There wasn't any operations research. There were just a few places that taught a few courses in statistics, but there was no ops research capability. Kids that come out today have all of these wonderful tools. But we had the opportunity that we got to go tinker with the hardware. We got to go out and touch the hardware. We got to see it. We got to feel it. We got to work with it. That's something, we had a whole generation of these bright young people. Again, I'm referring to Marshall. I suspect the same thing could be said at other centers as well. But certainly in Marshall, we had a group of really great people, but they did not have the experience of actually working with real hardware. And this was one of the objectives in doing the design. We were criticized. NASA took a lot of criticism because of the fact we decided to design the ARES 1 upper stage in-house and to do the integration of the ARES 1 stack in-house. Now, that was not intended to take, it wasn't because we needed the work. It wasn't because we could do it faster. It wasn't because we don't like contractors. It was done specifically to give our whole generation of bright young people, young future managers, hands-on experience managing real hardware. And I don't care how much you study about integration, how much you study about project management, that is not anything like having actual hardware to work with. You'll discover that there are problems that you could never, ever have anticipated. And to be a manager with any level of competence, you have got to have had experience, hands-on experience, managing and working with hardware. That was something the administrator wanted us to do, and that was our objective in doing it. It was nothing less. Now, it cost us some public relations because some people thought we were excluding our potential industrial partners by not offering them that opportunity. But we needed to get that experience, and that's why we did it. And it was successful to that extent. Then the next thing I want to talk about is anticipating problems. There will be problems arise that if you work to an ideal schedule, you don't have any slack in it, you're going to find problems that are going to come up that you just simply had not expected. One example of that I'm sure you've heard a lot about was the thrust oscillation issue on the first stage of the Aries 1. Now, characteristically, all solids have a certain pulsating nature to them. It's caused by vortex shedding within the case, and it's something like it's a long open cylinder. It's an organ pipe is what it is, and that gets amplified. Now, that turned out to not be a problem. We flew the 4-segment solids on the shuttle, and we didn't have any thrust oscillation issues. There was thrust oscillations. In fact, that's part of when you listen to the launch. In fact, when you're there tomorrow and you see the launch, you will hear that staccato sound, and that's associated with that variation in thrust. It goes up, it goes down. We've experienced that before in the past, and even with liquid engines. We had the pogo problems with the Saturn, but that's a phenomena that we didn't cause any real problems. It just made the ride a little rougher, maybe than they would have liked it, but that was all. It didn't really cause any serious problems. What we found when we took that, we had strapped 2 solids onto the side of the external tank, which was very stiff when it was pressurized, and that was attached to the shuttle orbiter, which is very stiff. So you had these 2 things attached to a very stiff structure. There wasn't much coupling. Now, when we put one of those solids and we put it underneath a upper stage in a long, slender thing, the natural modal frequencies are different. And what we found was that thrust oscillation was coupling with one of the natural frequencies, resonant frequencies of the vehicle itself, and that was causing what was initially feared to be very, very severe vibrations. Fortunately, 2 things happened. One was we found out that it had been the problem itself had been overstated, overestimated. It wasn't nearly as severe as we had thought it might be initially. Secondly, we found a number of ways to detune the frequency, and we even developed a new technology, which I think is just outright exciting, called LOX damping, in which we actually use the friction of the liquid propellant as a damper. And we were able to tune it and damp out those oscillations and make for a much smoother ride. Perhaps will be smoother than any solid motor that's ever flown because of that we had to do that. It wasn't an insoluble problem, but it was a problem associated with the fact we were using something that was already well proven, but we were using it in an environment that was different, a different kind of an application. That's something you have to watch, because something works in one application, it may work in another, but it may also introduce certain levels of problems. I noticed at the time that first surfaced, there's a thing we have today called the information age. Everybody knows everything instantaneously. And we heard deadly vibrations, we're going to kill the astronauts, all these kinds of things, which were absolute, pure nonsense. But nevertheless, it was, every time I picked up a newspaper, I thought they'd changed the name of our program from Areas to the Troubled Areas Program, because that's everything you read. It always started out with the Troubled Areas Program. Areas had less troubles than anything I've ever worked on. The honest truth is, we had the problem du jour during the Saturn days. You try to build 1 million pounds of propellant tank with a stage that has 1 million pounds of LOX hydrogen, man, that has got problems. We had serious problems that we had to overcome. So we did that, we solved that problem, but that's just an example. When you use hardware in a different way, you get different results. One other thing I'll mention in the way of those unexpected problems, I learned a new word during the Aries 1X program right at the end. Tribo-electrification. I had no idea what that was. I had never had any association with it that I knew about. I later found out it wasn't real complicated. It's kind of the same thing you have when you, in a classroom, when you rub two substances together that have different coefficients of dielectric coefficients, you know, like rub amber on a piece of animal fur. One takes on a positive charge, one takes on a negative charge. Same reason when you rub your feet in dry weather and you touch a doorknob or touch somebody, it sparks. You build up a charge, and that was abhorrent to range safety, because we didn't know about it because we fly the shuttle, and the shuttle's exempt from it because we would never do a range destruct. But in the case of the slender unmanned thing, range safety wanted the ability to send an abort command, and if there was an electrical charge built up, it might not get the signal through, and we might not be able to abort when they wanted to abort. And that was scary, but I'd look up at the Florida sky and might see a few wispy clouds 50,000 feet, but looked like a pretty clear day. Say the range is red. You've got tribo-electrification. So we learned a new word. It found out it's not hard to fix. You put conductive coatings. People said, well, is the paint on your vehicle, is that conductive or not? We said, well, we just painted it because it looked better. We didn't know about that. So we learned something. That's something you learn when you build hardware. You find out things. I'm not going to take a lot of time talking about the knowledge capture. I think that has been mentioned several times, and it's important we have a good database. What we learned during the Apollo program, we're trying to do a better job of documenting that today. Now talk just a little bit about Lean Six Sigma. That all of us have been exposed to some of the management tools from the past. We had continuous improvement, total quality management, business process re-engineering. Well, there were a couple of real powerful tools. One was called lean manufacturing, and that allowed you to do things quicker and with less manpower. There was another one called Six Sigma, which was to improve the reliability. We found that large companies like Boeing relied on that to streamline their manufacturing process. And the combined things called Lean Six Sigma. We use that. Every manager in the Aries project has been trained in Lean Six Sigma, and many of the working employees have as well. So that was very important. I think that's probably the main points. Other than I wanted to say just a few things about 3 issues that came up during the discussion. And I'm going to tell you in advance that the answer depends. It's kind of like Harry Truman said he always wanted to get an economist that only had one hand, because as soon as he asked him a question, he got an answer. He'd start to act on it, and the economist would say, but on the other hand. So this is one of those things, it depends. The first was question of reusable versus expendable. And I think it depends totally on the application. To try to build a vehicle of the class of a Saturn V and make it a fully reusable system or mostly reusable system probably would not be practical. On the other hand, I think the space shuttle, of which I am very proud, is a mostly reusable system, and it was the right thing to do. I think whether it's reusable or not reusable depends on the particular application. If you have high flight rates, then I think the problem with reusable systems is they generally have a large fixed cost, very low, relatively low recurring cost or marginal cost. The reason the shuttle never achieved its full goals in terms of cost was the fact that it was always had a low flight rate. If we had flown those 60 flights a year with 2 weeks turnaround and all that we talked about in the beginning, the economics would have worked. hey, I won my first Group Achievement Award justifying the shuttle's cost. I'm not going to give it back at this point or apologize for it, but second thing is, should we have abort or not abort capability? In the case of a long, skinny vehicle where the crew rides on top, you sure want a abort system. You want to be able, if there's a failure, an engine shutdown, whatever, you want to get the crew off. Does it make sense to take a vehicle like the shuttle and try to give it an abort capability? Probably not. Probably not a good idea. Probably not practical. So again, the answer is a definite yes. You may want to abort, you may not. Depends on the application. And then the final is, should we oversell or undersell programs? And I learned from one of the best on that, and the answer is both. Werner von Braun wrote a series of articles in the early 50s, I think 5 or 6 for Collier magazine. And those articles were read by a brilliant young man named John Kennedy. And he read about the vision that von Braun had, what we could do. When he became president in 1961, he immediately, and I have had the opportunity to screen that correspondence. He corresponded with von Braun. And he was looking at several things that could be hallmarks of his administration that would actually, be something he would be remembered for, and also something that would show the Soviet Union, the height of the Cold War, that capitalism could do something that communism could not. And he was considering the possibility of a sea level canal to replace the Panama Canal with its series of locks. He was going to have one at sea level that could flow from Atlantic to Pacific with no locks and the largest ships in the world go through it. Would have been impressive. He was looking at a massive irrigation project that would have turned some of the arid west into tillable farmland. And he was thinking of sending people to the moon. He corresponded with von Braun and said, Dr. von Braun, would you assure me, can you assure me that if I commit to send men to the moon in this decade, can you guarantee me that we'll accomplish that? Von Braun said yes. Was that overselling? He didn't know how to do it. We didn't have a Kennedy Space Center. We didn't have a Saturn V launch vehicle. We didn't have launch pads. We didn't have test facilities. We only had concepts. And we're talking about, he made this promise on the 20th of May of 1961. That was just 15 days after we flew Al Shepard for a 15-minute suborbital flight. It was a full 9 months before we flew John Glenn, the first American in orbit. And he committed to send men to the moon. Dr. von Braun, can we do it? Yes. That's why we did it. Von Braun had not assured him. He said, maybe we can, not sure, we need to study it. We would not have had the Apollo program. So he oversold it. Then, on the other hand, he promised that we could throw 99,500 pounds to the moon in the Apollo program. By the time we got through, the last Saturn actually threw about 108,000 pounds of payload above the S-4B, more than it was even designed to carry. If you've ever seen pictures of that last launch of Apollo 17 with Gene Cernan, Harrison Schmitt, if you ever saw that thing lift off, it looks like it's slow motion. That's actually how slow it is going. It had a thrust to weight at only 1.17 to 1. And that's because he'd had all these margins built in. And those margins saved him. And he ended up he not only did what he said the Saturn would do, he did more. So he oversold, but then he overproduced too. So I think the answer, again, depends on the circumstances, maybe both. Thank you very much.